We've taken a look at gravitational fields, the general concept of gravitational fields. Remember what a field is? It's a region in which a mass can experience a gravitational force. Right? Why do we talk about that region in which a force could be experienced? Well, because really, up until now, we've talked about just the gravitational force, and that's fine if there's something there to feel the force. If there's something there to experience a push or a pull, it's great. Talk about a force. But if there's nothing there to experience it, we can't do that. We can't talk about a force. We have to have some other way to describe gravity, which doesn't disappear when there's nothing there to experience gravity. Hence, a field. It's a region in which a force could be experienced if there was a mass there to experience it. We talked about two equations that describe gravitational fields. The first one we called the producer equation. The producer equation looks like this. Gm little g, the gravitational field strength, is equal to big G times m over r squared. Big G is the constant. R is the distance from the center of whatever it is that's the producer to wherever it is that you're trying to find the field. Tell me what m is. And I'm looking for an answer that's a little bit beyond the most simplistic answer here. Rosie, tell me what m is. Good. It's not good enough just to say mass, because sometimes you're going to be given the mass of the producer and the mass of something that's experiencing the field. You need to know which one to use. Rosie, you're right. This is going to be specifically the mass of the producer, and it's always going to be in kilograms, just as R is always going to be in meters. Whenever you have information about what causes the field, the producer, which is often going to be like, say, the Earth or another planet, then you're going to use this equation. Whenever you have something about, information about what experiences the field, you're going to use this equation. G is equal to F over M. That's a simpler equation, but it's in some ways a little bit harder. Why? Well, because first of all, you have to recognize which mass to use, just as you do in the first equation. This would be, by the way, the mass of the experiencer, not the mass of the producer. The mass of whatever it is that's feeling the field. The mass of whatever it is that's being pushed or pulled in kilograms. But this, you have to be careful with this. It's not just any force. Okay? You can be given a force that's not relevant to the question. This is specifically the force of gravity acting on the experiencer. What's another name, another term for the force of gravity acting on the experiencer? Weight. The weight of the experiencer. So if you happen to be told, here's the force of gravity acting on it, or if you happen to be told, here's the weight of the object experiencing the field, then that's probably what you're going to use. The units for that, by the way, are going to be newtons because it's just a force. The units for gravitational field strength, there's actually two units that we can use. One comes from this equation, force over mass is newtons over kilograms. What's the other units that we can use as well? This goes back a long ways. What's the other units that we can use for that one as well? William, do you know what the other units are? Nope. Not quite meters per second, but you're close. Meters per second squared, because really the gravitational field is the acceleration due to gravity. It's just that we sometimes don't call it that anymore because in the context of the field surrounding the Earth, there's not always something accelerating, right? We talked about the acceleration of gravity as always being roughly 9.81, but if there's nothing accelerating, then the acceleration due to gravity maybe isn't the best term to call it, the best name to give it. All right, you got information about both of them? Use whichever one you want, because in the end, my board marker is held 1 meter above the Earth. The gravitational field that's caused by the Earth at that point is the exact same value as the gravitational field experienced by the board marker at that point. They're both the same, right? If you're dealing with the field at the same point, the values are both the same. So which one you use doesn't matter unless you don't have information about one of them, right? Pick whichever one you have more information about. If you've got information about both of them, use whichever one you want. One more final little thing before we check over the questions that we had for homework last night. If you don't happen to know which one to try, right? You're looking at this question, you're like, I don't know, I'm not sure which one I should try first. It's just like those group B equations that we learned early on this year. If you pick one and it's the wrong one, you're not going to get the wrong answer. You're just going to end up with 2 or 3 unknowns. And that's okay. What do you do when you end up with 2 or 3 unknowns? Try something else. Right? So if you happen to try the producer equation, it doesn't work, then try the experiencer equation. As long as you use the right data with the right equation, it doesn't matter which one you try first. Really, this might mean a bit of extra work, that's all. All right, we had 2 sets of questions that we worked on yesterday. You worked on these ones in class, and I think you guys all finished these in class. Were there any issues with these on page 218? No issues with 218? All right, the second set of questions that you had was on page 220. And those are the ones that that I left you with for homework. Any issues with those questions on page 220? 2B? Okay, since we're going to do 2B, we'll do 2A as well. We'll just do question number 2 from the start. Anybody for 1 or 3? No? All right, 2 it is. I guess 2A is just asking for a kind of an opinion, I guess. But do you think your skeleton could support your weight on Jupiter? Who says yes? Jupiter's heavier than the Earth, by the way. Jupiter's bigger than the Earth, right? It's more massive than the Earth. Okay, who thinks your skeleton could support your weight on Jupiter? Okay, nobody? Who says no? Okay, lots of people say no. Okay, we'll see here. So the consensus seems to be no, though, that your skeleton couldn't support your weight on Jupiter. Let's see how much stronger your bones would need to be on Jupiter here. If I want to compare, or if I want to find out how much stronger my bones need to be on Jupiter, then I need to find out how strong gravity is on Jupiter compared to the Earth, right? Because in the end, my bones have evolved over millions of years to be able to handle the Earth's gravitational field of about 9.81. Okay, and I can do that. Okay, when astronauts go into space, okay, they're actually handling less than 9.81. Their bones haven't adapted to handle less than 9.81, but if you were to go to Jupiter, they haven't adapted to be able to handle more than 9.81 either. Okay, let's see how much stronger my bones would need to be. To do that, I want to find out how much stronger gravity is on Jupiter than it is on the Earth. Okay, the first thing I'm going to do is find the field strength caused by the Earth. We know that we're going to get somewhere around 9.81 for this, right? 6.67 times 10 to the minus 11 times 5.98 times 5.97, I think it is, times 10 to the 24 times, or divided by 6.38 times 10 to the 6. Okay, gravitational field strength caused by the Earth. Earth is a producer, right? Is there an experiencer on the surface of the Earth to feel this? Maybe, maybe. If there is, we don't know anything about it. So we've got to use the producer equation there. Does anybody have a value for that? I know it's going to be around 9.81, but actually I think it was 9.78 when we did that. 9.78, we're going to say newtons per kilogram, but we could have just as easily said meters per second squared. Both would be correct. All right, let's get the gravitational field caused by Jupiter now. That's going to be G times the mass of Jupiter, same big G, but different mass and different radius here. 6.67 times 10 to the minus 11. From that table, I don't really feel like flipping back. So from that table, does anybody have the value of the mass of Jupiter? I don't know what it is, but I know it's going to be bigger here. 10 to the 27. So we're looking at about 500 times more than the mass of the Earth. Radius of Jupiter. Ben, you got that one? 7.15 times 10 to the 7 meters. All right, so look at this. It's heavier. It's a lot heavier, right? Which is going to increase gravity, but it's also bigger. It's a bigger radius, which is going to decrease gravity. Now, I have a feeling that the mass is going to matter more because we're increasing the radius by about a factor of 10, even though it's squared. We're increasing the mass by a factor of about 500. I think the mass is going to matter more here because we're increasing it by a lot more. Who has the value for the acceleration due to gravity or the gravitational field strength on Jupiter? You get 24.8 meters per second squared, or I'll go with newtons per kilogram just to be consistent with my first answer, but meters per second squared is just as good. All right, you want to find out how much stronger your bones would need to be. Let's divide the two. Let's say 24.8 newtons per kilogram divided by 9.78 newtons per kilogram. And I think we're going to end up with somewhere around 2.5, 2.53. So, no, clearly we wouldn't be able to survive that. Our bones wouldn't be adapted to that. Could we, for a brief time, like for a little while, be able to be supported by our bones for that? Sure, a minute or two, a couple minutes, we'd be fine for that. But over a long period of time, there's no way that we'd be able to survive that. Or our bones, that is, would be able to survive that. Is there a hand up back here? Oh, good. Good there? All right, let's move forward to our last topic of the unit, called satellites. The reason we're going to talk about satellites for today is because satellites kind of tie together what we've learned this unit. The whole idea of gravity, which we've been talking about for the last little while, and circular motion, which we were talking about for the first portion of the unit. A satellite is anything that revolves around something else. Technically, as I walk around you right now, technically I'm a satellite of you. Although typically when we talk about a satellite, we're talking about something that orbits around something else because of gravity, not because of some force of friction between my feet and the floor. There's two kinds of satellites. One's called a natural satellite, which is something that occurs in nature, like the moon revolving around the Earth, or the Earth revolving around the sun, or any of the other planets revolving around the sun. Those are natural satellites. They go around the sun, or the Earth, as the case may be. They're held in orbit with that centripetal force by a force of gravity. It's the typical satellite that we talk about, except it's nature. And the other kind of satellite is what we call an artificial satellite, which is a satellite that acts exactly the same way as the Earth revolving around the sun, except that it's not natural. We've made it happen. For example, the ISS. You guys know what the ISS is? Yeah? Yeah, the International Space Station orbiting around the Earth. That's an artificial satellite. It orbits around the Earth at a distance of about 400 kilometers, just like the Earth revolves around the sun at a distance of about 1.5 million kilometers. Except that we've put the International Space Station there, and we didn't put the Earth there. You guys know that the International Space Station orbits around the Earth several times per day. In fact, its orbit isn't this consistent orbit. It sometimes orbits above one place and sometimes orbits above somewhere else. It sometimes actually orbits above Calgary. Everywhere in the world, it goes above at some point in time, just not necessarily every day, the same spot. You can actually click on spaceflight.nasa.gov, type in your city, and it'll tell you when to look and where to look. If we were to click on that website for Calgary, enter Calgary, we'd end up getting a page that looks like this. If we scroll down that page, we would see that the next time the International Space Station is going to be above Calgary and visible above Calgary. And by the way, when we say visible above Calgary, it's very visible. It's the brightest thing in the sky. Now, you can't see details. You can't see an astronaut looking out the window, waving at you, waving his or her flag. But you can see the space station. You can tell exactly what it is because it's the brightest thing in the sky by a lot at that point, and it's moving pretty fast as well. The next time that it's going to be visible in Calgary or Okotoks is Wednesday, May 11th. That's about 6 days from now. The problem is it's going to be 4:41 in the morning, and it's going to only be visible for 2 minutes. It's not a great viewing because it appears at 10 degrees above south-southeast. This is south, this is west, this is east, okay, over here. So it's going to appear down there somewhere in the sky in that direction, but it's going to be really low on the horizon, 10 degrees above the horizon. And its maximum height as it goes across the sky is only going to be 11 degrees. So if you want to actually see it, you want to look for things like this. Monday, May 16th, perfect. It's still pretty early in the morning. It's appearing at 10 degrees above west-southwest. So it's appearing over there, 10 degrees, so about this angle. It's going to be pretty low on the horizon. You may not actually see it appear on the horizon because it's so low on the horizon. But you can see that it goes all the way over to the east through the sky. You're going to see it go all the way over from here, all the way over to there in the sky. And it takes 5 minutes. So you're going to be able to clearly see it, 5 minutes. And its maximum height is 77 degrees. So although it starts really low on the horizon, by the time it gets over here to the south or to the southeast, it's way up there, really, really high in the sky at 77 degrees. That's a perfect time to set your alarm to get up at 5 o'clock in the morning and watch the International Space Station go over. Now, if you don't feel like getting up at 5 o'clock in the morning to do it, check back because this thing gets updated all the time, right? You're not going to see another good one. It's not early in the morning. There's a few good ones here, but they're all early in the morning. You're not going to see another one that's not early in the morning until, I don't know, until at least May 19th, until at least after May 19th. But after that, you never know, right? Sometimes it's, 11 o'clock at night. You see a really good one at 11 o'clock on a Saturday night or whatever, which might be able to stay up to 11 o'clock on a Saturday night to watch it, right? Check it out. Seriously, like you can't mistake it. Okay, if you know what you're looking for, you can't mistake it. All right, so that is an example of a satellite. It's an artificial satellite, but it behaves just like the Earth revolving around the sun does, and it revolves around the Earth for the same reason as the Earth revolves around the sun. We say down here that most satellites travel more or less in circular orbits, although when we say more or less in circular orbits, really it's usually an elliptical orbit, but it's close enough to a circular orbit that the analysis that we're going to apply is going to work for us. Most are held in orbit by gravity, which means that there is a centripetal force that is caused by gravity. Just like when the car was going around the turn, the centripetal force was caused by friction. When the Earth goes around the sun, the centripetal force is caused by gravity. So, as it always does, it seems, in physics, it comes down to an equation. Listen, we always go to math, right? Like, math is a tool that describes physics really well. But understand that physics is not just about math, right? We always go to these equations. But it's important to understand why as well, the concepts as well. And you guys know that from your multiple choice questions, right? And when you see those multiple choice questions on your unit tests, it's like, oh yeah, I got to know something beyond the math. So don't forget that. Just because we always go to the equations and we work on questions in class, don't forget that stuff like that is important too. And it's important not just to remember that, but to understand it. All right. Having said that, let's go to the math. When we talk about the motion of a satellite, we said it experiences a centripetal force. Centripetal force is mv squared over r, the force experienced by any object moving in a circle. And although a satellite isn't always in a circle, it's close enough that we call it a centripetal force. It's caused by gravity. So we're going to set those two forces equal to each other, the centripetal force and the force of gravity. The centripetal force is mv squared over r. And the force of gravity, we could technically say it's m times g, but we need to know what little g was there, right? So in order to find, hold on before you write this down, okay? In order to find a little g, we'd say it's gm over r squared. So if you're going to find a little g by this equation and then plug it into here and multiply it by another mass, you might as well just use that other force of gravity to begin with, which says gm1 m2 over r squared, because that's what you'd end up getting if you plugged gm over r squared into the m times g equation. Now, this is a little bit weird here. We have an r on both sides. In fact, we have two r's on the right side. Let's cancel out one of them. So I'm left with mv squared equals gm1 m2 over r. I got three masses here. Or do I? I really only have two masses. The mass on the left side is the same as one of the masses on the right side. But which one, mass 1 or mass 2? It depends upon what we call mass 1 or mass 2. I'm going to change those subscripts from mass 1, mass 2 to mass of the satellite times the mass of, we'll call it the mass of the producer. So if there's the International Space Station orbiting around the Earth, the space station would be the satellite, the Earth would be the producer. If we're talking about the Earth revolving around the sun, the Earth would be the satellite, and the sun would be the producer. Down to question? Yeah. What mass do I have over here on the left side? We're talking about a centripetal force, an object moving in a circle. What mass is that? The mass of the satellite or the mass of the producer? The mass of what's doing the revolving or the mass of the central body, which is being revolved around? What mass appears on the left side? What subscript do we want to add into that? Nick, what do you say for that one? MS or MP? Yeah, good. It's the mass of the satellite. Good. If the mass of the satellite appears on both sides, we can cross that off. And we're left with now v squared is equal to g times the mass of the producer, whatever it is it's being revolved around, over r. This is the basic equation for the speed of a satellite. It does not appear on your data sheet, but the good news is mv squared over r does, and gm1 m2 over r squared does. You just have to be prepared to put them together. In addition to this equation, you will sometimes use that other equation that we learned early on in this unit, 2 pi r over t. So maybe you're not looking for the speed of the satellite, maybe you're looking for the period of the satellite, in which case you'd have to plug in this expression into here. All right, let's have a look at a problem. Earth's moon is 3.844 times 10 to the 5 kilometers from Earth. This is from the center of the Earth. And you can see the diagram there drawn to the center of the Earth. If it was to the surface of the Earth, then that's not the number we want. We'd have to add in the distance from the surface to the center, right? In this case, since we have the distance from the center to the center, we're all good. Okay, that's what we want. Except that we do need to convert that to meters instead of kilometers. If the R value is 3.844 times 10 to the 8 meters, where did that come from? 10 to the 8 meters? 10 to the 5 kilometers, multiply by 1,000, get 10 to the 8 meters. Oh, we only got one variable here, solving for one, got one. If it's a satellite, in the context of a satellite, we will always say FC equals FG. We will always say mv squared over r equals gm1 m2 over r squared. We will always cancel out an r. We'll always cancel out an m. We're left with the mass of the producer on the right side. So v is equal to g times the mass of the producer over r. Or v is equal to the square root of g times the mass of the producer over r. All right. Let's see how fast the moon is really going around the Earth. I get 6.67 times 10 to the minus 11 times the mass of the producer, which is the mass of the Earth. It doesn't matter how heavy the Earth is, or sorry, how heavy the moon is here. Okay, the mass of the Earth, the moon cancels out. We're concerned with how heavy the Earth is here, the producer. 5.97 times 10 to the 24. Divided by that R, which is 3.844 times 10 to the 8 meters. Let's square root that. Let's pull out our calculators and do this together here. I get 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24 divided by 3.844 times 10 to the 8. Don't forget to square root it. When you do, we get 1017.8 or 1.02 times 10 to the 3 meters per second. When you look up in the sky at nighttime and you see the moon is moving. How fast is it moving? 1,000 meters per second, 3,600 kilometers per hour. We're talking about Mach 3.5. Why do you not hear a sonic boom every time the moon goes by the Earth? Right? When things go faster than the speed of sound, there's a sonic boom, right? Why do you not hear a sonic boom with the moon? Good, because space is a vacuum. First of all, you don't get the disturbance that causes a sonic boom. Second of all, even if there was a noise, it wouldn't be transmitted through empty space, right? So for two reasons, we don't hear that sonic boom. There's not one made, and even if there was, it wouldn't travel through empty space. All right, let's see what we can do with these two questions, please, on page 278. So then, the moon Miranda orbits Uranus at a speed of 6.68 times 10 to the 3 meters per second. So that's pretty fast, eh? It's pretty fast. You go around Uranus like that. Use this speed and the mass of Uranus to determine the radius of Miranda's orbit, keeping in mind the whole time that the mass of Uranus is 8.68 times 10 to the 25 kilograms. So what do we got to do here? It's a satellite problem, right? Where we got a moon going around a planet, and it's held in orbit around by a centripetal force, which is caused by gravity. So we're going to set Fc equal to Fc equal to Fg, the force of gravity. mv squared over r will be equal to gm1 m2 over r squared. Notice in each of the problems that I've done so far with this, I've derived the equation. The reason I'm doing that is because it doesn't appear on our data sheet, right? mv squared over r, gm1 m2 over r squared does appear on our data sheet, but the combination of them does not. So I'm deriving it every time because I know, like, if you're anything like me, listen, you get to a final exam in a couple months, you're going to forget that equation. There's no way you're going to remember that equation, but you are going to be able to hopefully remember how to figure out that equation if we go through that enough times. All right, we're looking for the radius of Miranda's orbit, so we're going to take that up by multiplying, take the v squared down by dividing, and we end up getting g times the mass of the producer over v squared. So it's going to be 6.67 times 10 to the minus 11 times the mass of the producer, which is 6.68 times 10 to the 3, divided by the speed. No, that's wrong. 8.68 times 10 to the 25, right? The mass of the producer. divided by the speed squared, which is 6.68 times 10 to the 3. So we want to make sure that we can square that, do everything on our calculator. So let's take a look up here and we'll do it. 6.67 times 10 to the minus 11 times 8.68 times 10 to the 25 divided by, let's use some brackets on the bottom, 6.68 times 10 to the 3 bracket squared. You get, what is that? Man, count decimal places. How easy is it to mix up when you're counting? Like, count wrong? Here's a little trick. Let's change it to scientific notation. Now let's multiply that by 1. 1.297 times 10 to the 8. Or 1.30 times 10 to the 8 meters per second. I just didn't feel like counting to get the exponent there, okay? So, little trick, if you have a whole bunch of places that you have to count, you think you might count wrong, then just convert it to scientific mode. Now I want to go back to degree or to normal mode now. There we go. All right, is that good? Let's take a look at another question then. 5.12 on page 279 says Landsat is an Earth imaging satellite that takes pictures of the Earth's ozone layer and geological features. It orbits the Earth at a height of 912 kilometers. So we have no worries about a collision with the International Space Station that orbits Earth at about 400 kilometers because it's more than twice as high. Now, theoretically, we could see this Landsat satellite from Earth as well. It orbits around, it reflects light from the sun. We could see that the same as we could see the International Space Station. But because it's higher up and smaller, our odds of seeing it would be significantly smaller. What's the orbital speed and its period? All right, we have to go an extra step on this one to find the period here. We know that Fc equals Fm. This is, sorry, G, Fg. This is what we do. We derive the equation. We cancel things out. Left with V squared is equal to G times the mass of the producer over R. And we want to find the orbital speed. So we're going to say V is equal to the square root of G times the mass of the producer over R. What's the producer here? It's the Earth, right? The Earth is causing the gravitational field. Easy enough. 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24. And it's on your data sheet. It's also on that table that you were given for your practice test in your textbook. Divided by R. Don't forget to convert this. 912,000 meters. Is that right? Is that right? What's wrong? Exactly. Exactly. Okay, that's the distance above the surface of the Earth. We talked about this a little bit already, right? Not in the context of this question, but earlier on. If you're given the distance above the surface, it's not what you want. You want the distance to the center. So you have to add the distance above the surface to the distance from the center to the surface. In other words, the radius of the Earth. So let's say 912,000 meters plus 6.38 times 10 to the 6, brackets, square all that. This becomes really ugly to do in our calculators. Sorry, we're not squaring it. No, that's right. We're not squaring it because we canceled out the square there before. So that does make it easier, although it's still a little awkward to do it in your calculators because it's an addition on the bottom. You got to be careful to use brackets there. Not as bad, though, as when you're squaring it. So let's say 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24 divided by, and let's use some brackets for sure on the bottom, 912,000 plus 6.38 times 10 to the 6. We get 5.46 times 10 to the, what is that? 1, 2, 3, 4, 5, 6, 7. But again, if you don't feel like counting that, you think you might make a mistake with that, just convert it to scientific mode and then multiply it by 1. That didn't work. There we go. Multiply that by 1, and look at what we get, 5.46 times 10 to the 7. Yep. Oh, but I got to square root that. Oh, would you look at that? No, you know what? Actually, I should have noticed that. Not only because I should have just square rooted it, because I should have caught that. Right? I should have noticed that when I got my answer, because that speed is way too high. Okay, when I get 10 to the 7 meters per second, it is possible for something to move that fast, but it would be incredibly unlikely for anything, especially that size, to travel that fast. That's more than 90% of the speed of light. Okay, and satellites are not going to be traveling 90% of the speed of light, right? That just doesn't make sense. I just wasn't thinking that. So we do need to square root that, you're right, which is going to give us a much more realistic answer. Let's say second function, square root. Now we get 7.39 times 10 to the 3. That's much better. Thank you for that. 7.39 times 10 to the 3 meters per second. So we're talking about 7,400 meters per second as opposed to 7 meters per second. That makes much, much more sense. Still fast, right? But it makes much more sense. All right, let's find the period now. Remember I said when we introduced this that we have another equation that we can use here as well, 2 pi r over t. Very first equation we learned in this unit, in fact, not the first one, but almost the first one we learned in the unit. Rearrange that, 2 pi r over v gives me the period. So we get 2 times pi times r, which is 912,000 plus 6.38. Divided by the speed. Now, I should have used the unrounded number for the speed. I just don't remember what that is because I didn't write it down. Okay, on a test, you should write down that unrounded number just in case you need to use it later on like this. Okay, until we get a final answer, it's always going to be unrounded. Let's figure out what this is now. Let's say 2 times pi times some brackets, 912,000 plus 6.38 times 10 to the 6, and the bracket, and let's divide it by the speed. I've got written down there 7.39 times 10 to the 3, but I've still got my unrounded number in my calculator, so that's the number I'm going to use. I'm going to divide by that unrounded number, and I end up getting a period here of 6.20 times 10 to the 3. What would my units be here? If I use standard units through this whole question, then I'm going to get standard units for an answer, right? 6.20 times 10 to the 3 seconds. So 1 year is the time that it takes the Earth to go around the sun. If we're talking about a Landsat year, in other words, the time that it takes a Landsat satellite to go around the Earth, it would be 6,200 seconds. So we're talking about 2 hours. So 1 Landsat year would be the equivalent to about 2 hours on Earth. All right? We're going to give you a few questions here. You can imagine what the difference is going to be between these and your last set of questions. Not much. What was the only difference between this and my last example? That radius, right? I had to add in the radius of the Earth here because we were given the distance above the surface. So be careful about that. When you're looking at a question, know what you've got. Do I have the distance to the center, or do I have the distance to the surface, and I have to add the distance to the center here? Okay, take a look at these ones on page 279, please.